Okay, I think we've had an hour to read this section, and I thought we'd take a little extra time because it's only, it's 10 pages, but it's pretty dense material. So I hope everyone had enough time to get through it. Um, are there any questions that you might have written down while you were reading it, or that you might have made a mental note of while you were reading it? Uh, no questions. Hmm.
It's not that some of the issues are not very clear, but I thought that when we go through the chapter together, things may become clearer. So for example, I was a little bit unclear about this kernel trick. I think we have done it earlier, but somehow I need to refresh the details. And of course, what's going on with LLE.
Sure. Okay, we'll go through that, and hopefully you, just save the questions that you have. Hopefully people have written down questions while you were reading. You should write down questions or make note of points that are difficult, because not everyone, I'll just speak from my own experience. When I read this stuff, sometimes it takes me 2 or 3 times to go through it before I get it, but I make a note of questions. I didn't understand this, and let me see if I can understand this better. And um, you know, no one understands everything at first glance. So you're expecting to have issues where there's something you'd like better explained or something, and those are the things you should make note of and use this discussion to try to get to the bottom of. Okay. Okay. So since there's no questions, let me just start with uh, the first section, using PCA to compress the Mnist data. Have people been able to use my Colab notebook? I'm just hoping it's that it works when you click on it and that you can actually use it.
Yeah, it works.
Okay, great. So I've basically gone through, and I mean, this is an excellent notebook to start with, but I just kind of went through and reorganized it to my own satisfaction, and so I just sort of numbered sections and so on. It's not anything fantastic, but I rewrote some things and I wrote comments about other things. But anyway, so the first thing he's doing is he's using PCA to, he's showing how PCA can be used for compression. That's one of its major uses. So, the whole idea is you're compressing the data from a high dimensional space to a low dimensional space so that A, it takes up less memory, and B, it will be quicker in your training routines because it uses less compute. All right, so the first thing we're going to do is we're going to load the Mnist data. You've seen how to do that before. And then he makes this point of, let's see if we can find the number of principal components that we need to explain 95% of the variance. Does everybody know what is meant by explaining 95% of the variance? Or are there any questions about that?
That's the same idea as R square, right?
It is similar to R squared. So the data sits in this high dimensional space, and the variance of the data is basically the sum of the square. It's the average of the sum of the squares of the data point minus the mean of the data. Okay, so it's basically the mean of the data point minus the centroid squared. So it's basically showing like how much spread there is in the data. And so principal components is doing, it's nice to think of it in two ways. One, it's projecting the data to a lower dimensional space such that for that dimension, the reconstruction error is the minimum. So if you decide that you have a three-dimensional data set that you want to project to 2 dimensions, then PCA will choose that 2-dimensional subspace for which the reconstructed data, that is, you map it down to the 2-dimensional projection and then you project it back, you map it back to the 3-dimensional space, but of course incurring losses. But when you compare the reconstructed 3-dimensional data set to the original 3-dimensional data set, that error is minimized. So it's choosing the two-dimensional projection, the two-dimensional space that minimizes the three-dimensional reconstruction error. That's what PCA does. And so that's one way to look at it, is as projecting to a space which minimizes the reconstruction error. Another way to look at it, which is completely equivalent, is that it will find the space that it will find the rotation. PCA finds the rotation of the data such that it has the maximum variance along one of the rotated directions. So you saw that example where we had this long, skinny data set in two dimensions, and we found the rotation to project it into one dimension along the direction of maximum variance. Maybe it will help to go back up and look at what we did before. Remember that the very first one-dimensional example that we did. It wasn't really, this was just sort of qualitative. We didn't really do PCA here. We just said what would happen if we did PCA. So we have this two-dimensional data set but it's correlated, so it's stretched out here. So PCA, we said, would find the rotation that would give a maximum variance along one of the rotated axes. And you see what I mean by maximum variance. It's the maximum spread along this axis. Okay. So that's the second way of looking at PCA. And again, these plots that he makes are really useful. I sort of blew this one up so that, because you couldn't really see it, what was going on in this plot. Now this is the case where the plot is actually coming from real PCA. So we start out with this three-dimensional data set, the red points, and then we find the two-dimensional plane for which, when we map the data to the two-dimensional plane and then map it back to the three dimensions, the reconstruction error, that is some of the square differences between the data points and their reconstructions is minimum. So that's this plane we're mapping to the PCA finds this plane that we shaded in gray. Okay, and in three dimensions, the reconstructed points are these gray points that are on the surface of the plane, and the reconstruction errors are these little. Okay, so here's the original points, the red. The gray points are the reconstructed points. That is, we map the data down to this two-dimensional plane, which then looks like this. That's the mapping to the two-dimensional plane. And then we map it back up to three dimensions, and that's this. So these gray data points are the reconstructed data points. And when we compare them with the red data points, you can compute the sum of the squares of the differences, and that's the reconstruction error. The mean sum of the squares of the differences.
Joseph, aren't the gray ones just the projections on
yes,
that
they are.
plane?
That's what I said, yeah. The gray points are these points. See, this is showing it in two dimensions, so this is sort of showing the two-dimensional plane with the data points mapped onto it, right? But now you want to map that back up to three dimensions, and that's what this does.
So which the reconstructions are not shown here, right?
Yes, the reconstructions are these grayed out points, these gray points here. These are the reconstructions. They lie on this gray plane.
The gray ones are the projections, right? That's what we said earlier.
Yes, that's what these are, the projections. Okay, because when you're projecting to a low dimensional subspace, right? So now we're projecting the original data to a two-dimensional subspace, and that's what this projection looks like. Now, when we project these points back to three dimensions, then
they are still the same points, right? They still
the
lie
same
on the
points.
same 2D plane.
Right, but now we're seeing that plane in the context of three dimensions, of three-dimensional space. So we basically mapped this subspace back up to three dimensions.
So would reconstructed points always lie on the same plane? I mean, on the same hyperplane in general?
Yeah, in a three-dimensional problem, yeah. If you're mapping from 3 to 2, and then you map from that two-dimensional plane back, those points are the same ones.
Shouldn't reconstruction be the gray to as closest to the red points that you're
Yeah,
thinking?
that's what I thought. Yeah.
Okay.
They are. They're as close to the red points as you can get in this two-dimensional.
Right. So, but that's the projection, right? So if we're talking of, if you do the inverse part of PCA, you will get points which are back in 3D, but they won't be exactly on the red dots.
That's
Okay.
exactly what you're seeing in this plot. This is the point. These are the points in 3D that are mapped back from the two-dimensional projection, mapped back to 3D, and these are the points that are optimally close to the original data set.
But this is
Joseph,
not
if you
reconstruction, right? This is
Joseph, if you look at page 225, sorry, there is an equation x recovered is equal to x d projected multiplied by the transpose of WD
Yep.
on page 225.
Yeah.
So
Here
the
is.
recovered,
So I've done it here too. So,
so
but
it's
let's go back to your page 225. Okay, so you're talking about page 225.
equation 8.3.
Yep, equation 8.3.
So x recovered is different from x d projected.
Yes,
You
that's
obtain x
correct,
recovered.
because XD projected is the two-dimensional projection. That's this. Okay, you get this by multiplying by that.
Okay,
He
okay,
calls it a, yeah. So let me just go through that process because it's
okay.
useful.
You are just getting the original coordinate spaces as opposed to just the coordinates on the 2D plane. I think, yeah, I think I got
Yeah,
it.
so you map them to the two-dimensional plane. So now you've got this is the lower dimensional mapping of the data. You reduce the dimensionality by mapping your 3D data to this two-dimensional data set. Now you want to reconstruct the data, so you have to take this plane and map it back to where it was in 3 dimensions. And that's what this does. So now these gray points are the same as these points, and this is the plane for which the data is optimally close. This is the hyperplane, the two-dimensional plane for which the projected data is
Okay.
optimally close to the original data.
So, am I right in saying that the projected points and the recovered points are actually the same points in space?
No,
Uh,
these are the, yes, I'm sorry, you are correct.
yeah.
But these are the projected points, and then
Right, but
when you
in
project
space
them
they
back to
lie on the
3D,
same
yes,
one, right?
these points, these black points are the same as the black points here.
Yeah.
Yeah,
Okay.
okay, I hope that's clear. So then, but let's look a little bit more at the mathematics, because I revised the notebook to try to show that clearly. So we have this, he calls this matrix C, let's see, projection onto the lower dimensional subspace. Where does he do that with it? I have this matrix. Yeah, here we go. This is where I discuss it. So, so this is the first process, project the data onto the first two principal axes. And the way you do that is you multiply it by this C matrix, where the C is the first two rows of V transpose. To get the two-dimensional projection that we showed down below that you've been looking at, let me just run there for a sec and just refer to it really quickly. This is the two-dimensional projection, right? To get there, we had to. Somebody isn't muted. Let's see now. Participants, mute. Okay. Anybody that wants to speak can unmute themselves, but I've muted everybody. Okay, where were we? Back up to here. Yeah, so the first step is to project the data down to that lower dimensional subspace by using the principal components. And remember, the principal components come from that V transpose matrix. They're the first two rows. If we want the first two principal components, we use the first two rows of V transpose, where V transpose is the matrix that comes out of singular value decomposition. Sorry for skipping around so much. I just want to refer you back to the equation. This is how you decompose the matrix X via singular value decomposition. Remember, it's a product of three matrices, U, S, and V, V transpose, where V transpose is the one we're interested in now because that's the one we get the principal components from. And then remember, S is the one we get the variances from. So let's go back to here. And yeah, and so here's where I show how to project the data down to the two-dimensional subspace by multiplying by this matrix C, where I'm defining C as a matrix whose columns are the first two principal components, which are the first two rows of V transpose. So basically, you know, you take V transpose and you transpose it back till you get V. And then this matrix C is basically the first two columns of V. Okay, and then to get the projection, you multiply the original data by this matrix, which has the principal components in it. Okay, so that's one step, right? And then the next step is to reconstruct the 3D data, which means you want from the 2D projection, which means we want to map the 2D data, the 2D projection back to 3D. So how do we do that? Well, we multiply this 2D projection by C transpose. And that means the original data is multiplied by this matrix C transpose, which I call the projection matrix because that's the way it's called in the literature. So if you take the original data and multiply it by the projection matrix that comes out of SVD, you get back the reconstructed data, which is your best estimate from the original data after you projected it down. So it's kind of like passing data through an encoder and then a decoder. You lose information when you do that. So the reconstructed data is not expected to be exactly the same, and that's what we saw in the red points versus the grayed out points. The original data was the red, and the grayed out points were the reconstructed data. So I hope that makes it clearer to everybody what's going on in this diagram. Yeah? No?
It does, yeah, thank you.
Okay. Okay, so now let's move on. Back to the Mnist data. Now we were looking at the Mnist data, and he shows that now we were talking about explained variance. So when you do this principal components analysis, you're finding a rotation that changes it basically rotates you into a new coordinate system in which the variances sort of are in a monotonically decreasing sequence over the principal directions. And so the first principal components have large variances associated with them, but then as you go on, the variances associated with the successive principal components decreases and decreases and decreases. And at some point, it becomes sort of, you can say, well, I don't really need to get the reconstruction that precise, so I can go down to it. I can figure out how low of a dimensional space I can go to. One way to decide how many principal components you want to keep is you can say, well, I have this idea in my head that I want to account for 95% of the variance in my original data. If I can find a new rotated coordinate system in which I can capture 95% of the variance of my original data, then I'll be happy. So you do this and you find out that how much does it take, how many dimensions does it take, how many principal components does it take to capture 95% of the variance? And it turns out that 154 components will do it. You basically find you're plotting the number of principal components versus the explained variance. And then you just find the place, the intersection where this is 95%, 0.95, where does it intersect the number of dimensions? And it turns out to be 154. So now you know you only need 154 components. So it's kind of interesting because PCA has several ways you can call it. You can, oops, I did something to that. There. You can actually specify the number of components directly by, you can say, I want 154 components, or you can say n components equals 0.95, which on the face of it seems ridiculous because n components is supposed to be an integer, right? But and so it doesn't seem to make any sense. But the interface of PCA understands what you mean. It understands that you want the number of components that leads to capturing 0.95% of the variance. And so it will do that for you automatically. And there it is, 154 principal components explain 0.95 variance of the data. So,
Joseph, I've got
yeah.
a far less interesting question. With just regards to sklearn, is there a good rule of thumb that would help to explain why sometimes we have, and maybe this is covered in some of the earlier chapters, why sometimes there's just a fit and sometimes there's a fit and a transform, and a rule of thumb to figure out when you use one versus the other?
Well, when you're fit just builds the model for you, but then if you want to take the data and transform it, you have to do transform it. Then you have to do fit underscore transform, or you can do fit dot transform. I think it does. So
No, I don't think there's a fit dot transform. I think it's either
fit
fit or
underscore.
fit underscore transform. But I'm trying to understand. There are many cases when you just have a fit, and sometimes there's a fit and a transform. And I get what the fit does. It's just, if there's a way to mentally try and wrap your head around why there might be a transform component.
Well,
there.
there's always going to be a transform, right? Because you have to transform the data to the model, right? I mean,
You usually fit on your training. So let's say you're finding your mean and your standard deviation or something of that sort. So you want to do that on your training set. Now, let's say you're doing it on your validation set. You don't want to recalculate mean and variance on that validation set. So what you're trying to do is you're going to use the mean and transform from your training set and just use transform for your validation set. So that is like one instance where you would use fit and transform for your training, but only transform for your validation.
that's a very good explanation. So thank you for that, Rekil. So the fit part just does what Rekil said. It fits to the training data, and then that all the information from the fit is then available. But if you actually want it to transform the data, the training data, then you have to do fit transform of the training data. And then if you wanted to apply that transform to the validation data, then you'd have to do the transform on just the validation data.
Fit underscore transform just calls fit followed by transform.
That's right. And I think there's a dot. I think you can do dot transform. I think you can do PCA dot fit, and then after that you can do dot transform. I think. Maybe I'm wrong. So that way you can do those two operations separately.
Okay, apologies. Now I know what you mean by the dot. Yeah. Okay, so fit. You call the fit function, and then you call the transform after that. Yeah. Okay.
Yeah.
Gotcha.
So to sort of dispel your confusion, you might just want to do a little reading in the sklearn docs that helps to sort of orient you about, because they're all of these models are built with the same API, so that you can accomplish the same things with the same commands for different models and so on. Yeah. So, okay, where were we? So then I thought, okay, let's, as a data scientist, it's interesting to try to understand, yeah, 154 reconstructs the Mnist data with 95%, capturing 95% of the variance. But as a data scientist, it's interesting to know, well, how few dimensions can I actually recognize the digits with a lot less than 95% with a model that's a lot cheaper than that? I mean, how cheap can I go? How few dimensions do I need in order to still be able to recognize the digits? So I just slightly modified his code here, and I ran through multiples of 10, dimensions from 10 up to 150, and then displayed the results. And this is what you get. Here's the original data, which, as you know, is 28 by 28 images of the digits, 784 dimensions. But then, what if we start taking away dimensions bit by bit by bit, and you can see that not much is happening here as you go down from 150 to 80, and then you keep going down. You can start to see that it becomes a little more grainy and so on. But here's the things to focus on right here. 10 dimensions, you would say, or I would say, you can't. There are some cases where you can't distinguish the digits. You'll make a mistake on this one. You won't be able to recognize a 5 there. You won't be able to recognize that 8. So 10 isn't enough. And 20 is a little better, but it still isn't very clear. There are certain digits that can be confused. But by the time you get to 30 dimensions, I would say, it's easy to recognize all of those. So there's maybe if you look carefully at that, you see that it's an 8, but you might confuse it for a 3. 30 dimensions, 40 dimensions, 50 dimensions, this is really good enough for human beings to read this stuff. So that was kind of interesting to see. You don't really need 95% of the variance to be able to use these digits. So you can build a much cheaper model and still have it succeed. Okay, so any questions up to there?
No, that's a nice little experiment there. Thanks.
Yeah.
Can we go a little deeper into the idea of explainability? Because one of the things that's happening here, if you think beyond this Mnist data set, but think of data sets that have 300 different features, not images, but like other things.
Yeah.
And by doing PCA, we're able to drill down the idea of interpretability, explainability, drill down on features that are more valuable towards building a prediction model. Anybody have ideas or sort of experience around explainability through PCA?
As far as I know, PCA destroys explainability, because if you have 300 dimensions and you try to build, you do PCA, then your reduced dimensional space, suppose you're going to try to project 300 dimensions down to 5 dimensions or something to make it more explainable. Well, each of those 5 dimensions is a linear combination of 300 features. Those features, those 300 features might be very clear and you can understand what each one of them means, but no one is capable of understanding in their head a linear combination of 300 explainable features. So once you do the PCA, you've lost your explainability.
It depends on the data though, Joseph, because I've already posted the link, but I'll repost it. It gives the one link which explains PCA, has this exceptionally lucid explanation of how genetic variations in geography in Europe particularly can be traced using and analyzed using PCA, and he has a map and he has the PCA axes, and it's just phenomenal how accurately it matches that. Now, having said that, the reason I say it depends is if you apply the same thing to the US, it completely breaks down, because US's immigration patterns are, genetic patterns are based on time series and not so much the geographic distribution. So it depends on the data as to how much explanation you can have, because one of the foundations of PCA is that the axis of maximum variation is a source of your explanation. If that's true, then it will help explain. If that's not true for your data, it won't.
That's interesting. So are you talking about you're talking about human genetic data, or?
Yeah, I'll post that link, and it's fascinating to see that map and the corresponding PCA analysis side by side. It's just incredible. But of course, it's a very specific example, but that just goes to show that it depends on the data, how much it can explain versus how much it can obfuscate. But the underlying thing to think about is if the axis of maximal variance, which is what PCA gets you, is something that explains your data, then PCA will help immensely. Of course, with the first one or two, by the time you get to even third or fourth, because of what I said earlier of everything having to be artificially perpendicular to everything before it, you lose the ability to explain. But the first two, very good. But it depends on the data. There are tons of data where the axis of maximal variation don't give you what you are after. And if that's the case, it won't explain. So it depends on the
That's a
data.
good point. Yeah. So I guess we saw this. So I guess I should take back what I said, is that it doesn't always destroy explainability, but it you know, like we had the example from Jeremy's class where we did PCA on movie reviews, and we found sort of ad hoc, retroactively, we found that, yeah, PCA has identified these features that human beings can understand. And, you know, in other words, we saw that maybe one of the features represented whether it was a horror movie or a romantic movie. PCA just identified that by magic. And then human beings have to come along and say, oh yeah, that's what this feature means. It must mean, you know, along the spectrum of horror to romantic movies. So sometimes, I think what Srinivas is saying is that sometimes you can go back and in an ad hoc manner, you could look at the data and say, oh, I recognize what this feature has done. You know, I recognize what PCA has done. But there's no guarantee that PCA is going to find something that will make sense to a human being. So that's one thing, and I think Srinivas said both things. It says that there's no guarantee that PCA will find something that is, will find new features that are understandable to human beings. But what Srinivas also said is that sometimes, in some kind of a serendipitous manner, PCA mysteriously finds features that do make sense to human beings, the first couple of principal components. So, yeah, there's that.
I would agree with Srinivas. I think that PCA is potentially useful, at least in the healthcare data case. You know, if you have a large, you know, if you have, you know, something with a lot of columns, okay, as we tend to have in healthcare data, you know, you can have 300, 500 features or whatnot. You know, the question is really, you know, can you simplify your model to gain something more from it? And PCA allows you to distill down that model to a few components. Now, granted, okay, it may not, you know, give you, you know, a perfect correlation. I mean, if you have, you know, a 50% correlation with 7 variables, you're kind of out of luck. But if you do a PCA and you're able to get to like, you know, 90, 95% with, you know, 4 or 5 components, you know, then you have a, you know, if you can investigate each of those components, and you don't get, you know, caught in the causality correlation trap, you know, you can actually, you know, distill some useful, you know, information out of that. It's just like reducing things to a linear model, you know, where a number of the terms drop out. It's not a perfect approximation, but it's a useful one.
Yeah, and so yeah, I think going back to what Srinivas said, if humans can go back and look at those new features created by PCA, and if they can make sense out of them, then you have a useful set of features that helps with explainability. But I guess the other side of the coin, which Srinivas also mentioned, is that there's no guarantee that that would happen in any problem. So that's a good point, Stephen. Let's see. So let's continue on.
So, Joseph,
yeah.
I've got 2 questions. One is
Sure.
around sklearn's API.
Yes.
Right. So you've got this PCA. Oh, where is it gone?
Am I showing the PCA API now?
No. So no, I think it's in the notebook anyway. So you've got the PCA. Again, I just want to understand if there's some sort of nomenclature that's used in the sklearn world, where you've got PCA.n underscore components, and then you've got PCA.n underscore components underscore. Does the trailing underscore mean something?
Well, yeah, it does. So let's do something then. Where are we with n components? Which frame are you looking at in the notebook?
It was from his notebook. So I thought, yeah,
Okay, that's okay. I'll just do this. Let's look at this model that we just built. Let's see. Let's just look at this. Oh, I want to look at the model that we built, which is, I guess, each time I do this. sorry, here we go. PCA. So I have the model is just called PCA. So let's look at it. Insert a code so. So you can always answer your question if you have a question about what comes out of a model. You can always answer your question by doing a dir of it on it, and that shows you all of the variables that are available to you. These are the ones with dunder score, you know, dunder, blah blah blah. They're internal, and so you don't usually want to worry about them. But these variables starting here, these are methods and variables that you can get, methods and I forget what you call them, variables that you can get at from the model itself. So here's what you were talking about: components underscore. And
no, I was talking about the n underscore components,
yeah,
and n underscore components underscore. Yeah.
Yeah. So there they are. There they are. So we can do these. We can figure out what they are by just interrogating the model. So here we go. Let's do this. PCA.n components. I just want to find out what its type is first. It's probably just an integer, but I don't know. Yeah, it's an integer. So, and now we can find out how long it is. Whoops. Sorry. I just don't want to print something that's very long. Oh, it doesn't have, okay, so it's just a single integer then. So n components is just a number, and we can get at it. And 2. So I guess that's because further down, I had executed a lot of this notebook, and so this PCA model isn't the same one that was executed in the cell above. But the point is, so I had been doing a model where there were only 2 components, sort of towards the bottom of the notebook. So now that's one, and then we can ask for the other one. PCA underscore n, sorry, PCA.
Sorry, so my question, so these are attributes, and my question was more
attributes,
along,
that's right.
In sklearn in general, if you have an attribute A and then you have an attribute A underscore, does that mean something, or is it just a coincidence?
Can anyone answer that? I don't know the answer to that, but I suspect that it's not just a coincidence.
Yeah, usually underscore is added when it's something that is gotten as a result of some calculation. So when it finds out the ideal number of n components after doing all the calculations,
components,
that is stored as with an underscore appended at the end.
Yeah.
So when some attribute is obtained as a result of calculation as opposed to user given, then you have that underscore at the end.
So the difference here, John, is basically if you go ahead and set n components, you will get back PCA dot n underscore components, and PCA dot n underscore components underscore will be the same thing because you asked out of 10, give me back 3 components. So there's nothing great about that. The difference is when you kind of change PCA's algorithm and you can set, like how Joseph was showing that explained variance, where you can kind of set 0.95. So if you set a number between 0 and 1, so let's say you want like 90%. So that's kind of like implying that you want 90% of the components back. So that time you're not explicitly setting what n components is. So n components underscore is going to calculate it. That's what Gautam is saying, that it's post calculation that you find out what n components, n underscore components underscore is.
Yeah, that's a very good explanation. Let's look at this. This is exactly what I think Rekul just said. So we're just going to wait for this calculation to finish, and then we will we'll get at that. So what you're going to find is if you ask for PCA.n components, you're going to get the input. You gave it this input, n components equals, and that's what you're going to get if you ask for n components. And it's not going to be a number, it's not going to be an integer, it's going to be 0.95. So, oops, I misspelled it again. Right, but if I ask for the calculated version, which is which has the underscore after it, then I should get 154. So that's a good example to illustrate the difference there.
Okay, excellent. Thank you.
Okay.
And the other question I had is, if you just go back to the Mnist bit, maybe I've lost the plot a bit. So to the diagram where you had all of the different numbers, the figure. Sorry,
Yeah,
this
here.
one. So how did we end up saying this is 784 dimensions? Because I know that there are 784 pixels that are used for to represent a number. How did that become 784 dimensions?
Well, because if you look at the, these 28 by 28 images, there are 28 squared equals 784 pixels.
Yeah.
And so you can think of each image as a vector in 784 dimensional space.
Say that
if
again.
that makes sense. Okay, if you take and flatten a 28 by 28 image, you get a vector of length 784, correct?
Yep.
Okay, a vector of length 784 is a point in a 784 dimensional space. It represents a point in a 784, right? Just as a three-dimensional vector represents a point in the three-dimensional space.
Okay.
Yeah, right. So we're going from 784 dimensional space for the full image,
right. Okay.
And we're finding out that with a very much smaller number of dimensions, we can basically use these images. Yeah. So this is image compression. All right, so now we're here. So now he talks about other versions of PCA, and this is really interesting. I hope we have time to talk. We probably don't have time to go into all the details, a lot of the details. But so there's times when you want to do PCA, but your memory isn't large enough. You have a large dimensional data set that can't sit in memory, in your memory. So there's this method, and I don't know how the details, theoretically, how it's implemented, but what it does is it splits your data into batches. And so instead of having like 100,000 examples, you can have batch size, batches of 100 examples instead. And then you can do PCA. Your memory is big enough to do PCA on smaller pieces. And so it basically works like this. You build a model calling incremental PCA, telling it how many components you have, and in this case it's going to be 154 or whatever, and then you process the batches through, but by doing this partial fit, by calling this partial fit method. So it knows that it's trying to fit, that it's doing the partial fit method. It's not fitting the whole data set, it's just fitting the batch, and then it's incrementally improving its fit each time. And then, so it goes through this loop, and at the end, it comes out with a model. And it took, I just timed this, it took 34 seconds to do this. And then you can see that it recovers just as before. Then he points to another method of doing this, which is instead of looping through the batches, you build a memory map, mapping memory into hard drive space, right? So you sort of store the stuff on your hard drive the way it would be stored in memory, and then you operate on that data set. And so instead of doing a loop, you first create this memory map, and then you just run this thing and on the memory map, and you tell it what your batch size is, and then you call. It's still incremental PCA, but now you're doing it with the memory map. And it doesn't seem to have a speed advantage. So I don't know why you would do it either one way or the other. Maybe with larger data sets, there's a speed advantage of one over the other. They both take about 34 seconds.
I think in the second one, you don't have to read the whole thing, right? You are reading it part by part from a file in your file system. Whereas in the first one, you already have read the whole thing and then you are batching it.
Yes. So I guess if you don't have space to store all of your data, then that first way would be the best way, right? Because or the second way, right? Your data is on hard drive and it doesn't have to be in memory. It maps pieces of the data into memory as needed.
Yep. Also, so in PCA, if you have new test data, you would just do transform on the new test data. So that's another example of where you would use just transform, right?
So if you've already built this model and then you have some new data coming
Yeah, you
in,
would do just transform.
yeah.
Yeah.
Yeah, and what about the other one? You can't do that with the other one as
You
well?
would do the same thing. Yeah, you would just transform again.
Yeah.
Once you have done all the fitting to the training data, I think once you see new test data, you would just transform it.
Yeah. So why is this important, right? Because if you're building a model in production, you want to keep it training. You want to keep training it because things always change. They call it data drift or whatever. Seasonality or any other reason. The data from day to day could have different distributions. So every day you want to collect. If you have a model, you might be collecting new data and making predictions on it, but you also might be incorporating it into your model to make the model better. So both of these things are possible with these incremental PCA techniques. So you can build a model and then you can incrementally improve it without having to retrain it from scratch. Okay, randomized PCA is another flavor of PCA. I don't know theoretically how it works, but it works. It's much faster.
So the previous assumption is that you're not fitting anymore on the new data that you're getting, and you just want to transform it, right? But that is not necessarily true.
Wait, we're going back to here, to the incremental?
The difference between like the fit, transform. I just wanted to bring up those 2 points there, that the assumption then is that your new data, you're just adapting it to whatever stats you've calculated previously on your older data.
Yeah, that's what you would be doing if you just did fit transform on a new piece of data.
You'd be doing the whole thing. If you're doing only transform, you'll be just using the stats calculated previously, right?
Yes.
And the other point about what Gautam said about the for loop, I think that's just the implementation here. If you just write that on a generator or a list, I mean, one of those things where it just yields, you're still reading only what is required. You won't be reading the whole thing out. So I guess both of them would still not read the whole thing in memory, would still be just reading what is required. I still don't know what the difference though between.
Yeah, I'm trying to understand the difference. If anyone has thoughts about that, please feel free to post them.
But doesn't the first one already have the entire array in a variable?
Yeah, that's what I'm saying. Like, that's just the implementation here, right? If you write that on a generator, then it would just yield the batch size.
I mean, yeah, so internally that might be what memmap is doing.
Probably, yeah.
Yeah.
Maybe, yeah, that's what, yes. Maybe the implementation here, yeah, makes sense.
So there's two different ways to accomplish incremental PCA. I'm still not sure in what situations you would use one or the other. Anyway, so here's another PCA algorithm. If you choose SVD solver.
Can I just say a little? I think the first one is when you want to do like online. So that's why you have a partial fit, while like if you want to update your model online. But in the second one is the case that you don't have enough memory to run all the data. Like it has like the same function as the one before, but it doesn't work if you want to do your model online, because you already have like all your memory in memmap and you are not including new ones.
I see.
While,
that makes sense.
While in incremental, you can add new batches of information and keep updating your model
with this partial fit.
Yeah.
Partial fit. Yeah.
And it's not only for lack of memory, but also for this latter case to update on an online mode, while the other one is more like, I like memory, so I'm just going to do this one instead of the other one.
But Carlos, isn't that directly what you're talking about, radically relevant to the attribute partial fit? So you could use partial fit in both cases and still you would be able to train online, right? Partial fit is the one which is letting you do the training online.
The thing that now with your question is that I don't know if memmap can be updated, or it's based on the, like, you can add more stuff to memmap.
I see.
Or it's only to the initial array or trunk of information.
Okay, I get what you're saying. Okay.
That's what I understand.
Okay, that makes sense. That the partial fit allows you to do the online learning, that is collecting new data and tuning the model without having to restart to refit it all from scratch. Okay, so then we have this randomized PCA, which is a faster method of doing PCA. I'm not sure theoretically what it is. Let's see what he says quickly about it. He says, okay, so to call this method, you actually specifically ask for randomized, but the way it's implemented is if you set solver SVD solver on auto, it will automatically choose the randomized method whenever it's a good thing to do so. And he says that here on page 225, by default, SVD solver is actually set to auto. Scikit-learn automatically uses the randomized PCA algorithm if M or N is greater than 500. Remember, M and N are the dimensions of the number of data points and number of features. I'm not sure which order that is, because some people use M for features and some people use M for data points, and so it's not clear which one he's talking about. But and then okay, so if M or N is greater than 500 and D is less than 80% of M or N, or else it uses the full SVD approach. So if you are asking for less than 80% of a full reconstruction, then it switches to this randomized method, which gives you a more speed. And the details of the randomized method are not discussed here. So, but I'm sure that if anybody's interested, you could follow it up. And then he says, if you want to force scikit-learn to use full SVD, you can set the SVD solver hyperparameter to full. So you have control. So let's see, I did that here. I think I can run. He didn't do that in this loop. He didn't set it to full, and therefore when I ran this the first time, it got the same results. See, he's doing three things. He's doing full SVD, then he's doing incremental SVD, and then he's PCA, and then he's doing randomized PCA. But since he didn't, or maybe I didn't when I ran this, maybe it had already been, the solver had already been set to randomized. So I explicitly set it to full here, and I'm going to run it again and see what happens. It doesn't take too long. So we see what it's doing. It's running number of components starting at 2 and then by 10 up to 154.
Joseph, while we're waiting for that to run, I've just got a, oops, sorry. Okay, I've just submitted a link. Just got a question around this, the actual implementation of this on in sklearn. As part of the, so if you look at the fit method, when you call the fit method, they actually, you're redirected to an underscore fit, where they then implement everything within within the underscore fit. And just a question out to anyone: why would you do that instead of doing all of the work within the fit? The docstring says dispatch to the right sub method depending on the chosen solver, but it's not obvious to me why you'd split something out in that way. So this is just,
I'm not sure what we're looking at here. What are we looking at here?
So if you do a search for fit, so def fit, so the fit method. Yeah, yeah, that's the one. Yeah, okay. No, just fit.
Oh.
John, without even before looking at the details, just observation or comment in general, whenever the internally, and you can look at even FastAI code and such for many such examples, when you have an external API like ffit, and then you internally have different fits depending on choice, then you make that an underscore fit, which says, because it starts with underscore, it's a private method in Python saying, I'm going to not expose this. And if what you described is accurate, all he is doing is saying I have many fits and I'll choose which one depending on the set of parameters, but the thing I'm exposing to you is without underscore fit. Does that make it clear?
It does. So I understand the bit about the underscore making it private, but why would you want to do it in this instance? That's the bit. That's what I'm trying to get at.
Yeah, without looking at the code again in detail, I am not staring at the code at the moment, but what I would venture to guess is the fact that Joseph just went through which solver he calls depending on the parameters D and number of components. If it's greater than 500,
exactly.
M and N, then
Yep.
blah, blah, blah.
Yeah.
So he'll probably be calling different underscore fits depending on the settings of those parameters. But he doesn't want to expose every one of those to the fit. So he just gives you a set fit, and then within that whatever code, he calls the relevant underscore fit. That would be my guess. I haven't looked at the code, but that's, if I were to venture a guess, that's probably what is happening.
Okay, can everybody see what I'm showing the page, you know, the document from the actual code? Can everybody see this? Yes, this is the page that John pointed to.
Yep.
Okay, so we saw that it defined this underscore fit method to return the object, the instance itself. That's what was done here. Now in fit transform, it's calling this method, and actually it's defining. Oh,
no, it calls it within. It calls it within fit.
Within fit.
Yeah.
Quick guess is that
Yeah, right here. But then there's also a fit method defined here.
It's above fit transform. 320 something.
320 something.
A little bit below. There is 336.
336.
Yeah.
Yeah. Oh, okay, right. So here, but this is the actual.
So 336 is the actual fit, but it's actually calling underscore fit in 352, and that's the bit I'm trying to get my head. I mean, what Srinivas says, I'm aware of the private bit, you know, of making those private and the implementation bit, but it still doesn't make sense to me why, if you're going to offer these different options. But go ahead, Reko.
Other thing, John, is that both of them, actually, if you see PCA under the hood is using SVD, right? So you don't want to write SVD twice. So you're basically kind of encapsulating the SVD solver as one thing. Then when you call SVD, it is also calling the SVD solver. And when you write PCA, it is also calling the SVD solver. So that is one more thing I think could be a reason.
Okay, that might make sense. Okay.
So you're writing like one code base and you're kind of referencing from two sides sort of a thing.
Well, here's what Rekil just said, I think, right? It's calling SVD.
Sharing, yeah.
So in some way underscore fit is the SVD method.
For that, yeah.
Yeah. Okay. So John, I don't think I have answered your question, but maybe Rekil did.
No, thanks. He's pointing me to something just to check it out. It's just yeah, great. Thank you.
Okay. Well, let's move on then. Okay. So we talked about randomized PCA and that it is automatically chosen. If you leave the SVD solver unspecified, then it will default to auto method, and it has an algorithm for when it switches from full to the randomized method, which we talked. That's talked about in the book. So then I think I was here. So I misspoke. Here it's doing this not iterating from 2 up to 154 by 10s. It's just doing it for the values n components equals 2, n components equals 10, and n components equals 154. And so here we can see the timings. The first one is a full PCA, and the second one is incremental PCA that we talked about, and this one is randomized PCA. He wasn't able, the way he implemented this, he couldn't get the label for the third one, but it's always randomized PCA. So you can see randomized PCA is like 5 times faster here, generally 5 times faster, except, well, 5 times faster with a small number of components, but then with a larger number of components, it sort of loses some of its speed advantage. And then incremental PCA, when you get to incremental PCA, you're paying a penalty because it's not being able to use all of your memory at the same time. Right, it's storing only part of your data in memory, and then it has to make more operations to accomplish the thing. But so if you have, a relatively low dimensional problem like this, you don't get, you lose by using incremental PCA. But if you have a higher dimensional problem, it could be such that you wouldn't be able to do ordinary PCA because you won't have enough memory. And then the only way you can do it is incremental PCA. All right, so then that's the speed comparison. Then he compares training time with number of samples. And this is weird because PCA, randomized PCA time complexity is worse with large number of samples. That's kind of counterintuitive. I would have thought that randomized PCA is faster always, but it's not. Okay, and then he compares performance. Well, it's the same thing. Let me just read this carefully. So the first thing he's doing, he's comparing PCA and randomized PCA for data sets of different sizes. Okay, understood that. And the next thing he's doing, he's fixing the data set size and changing the number of features. So now, okay, so you can see what the difference is. Here we're looking at, the data sets from zero to 500,000 elements. But now he says, okay, now let's fixate on a data set of size 2,000 and change the number of features. And you sort of got the same thing. Randomized PCA and PCA have the same training time. So I'm not really sure why one is preferred over the other. I really don't know. Now, we're definitely out of time. I've gone over by 12 minutes. So perhaps we can continue the discussion of kernel PCA and locally linear embeddings. Maybe tack it on to the beginning of the next meeting, if that's okay with you, Steve.
Yeah, I don't have a problem with that.
Okay, I'll try to be brief and not take up too much time for that.
Okay.
All right, everyone. So on Wednesday we'll get together, and Steve's going to take us through the beginning of chapter 9. On, let's see, what is chapter 9? It's unsupervised learning techniques. So this is going to be interesting. Okay, I'll sign off. Let people go where they need to go, and thank you for being here.